So I'm going to try to shift to sharing slides. Okay. Okay, so what I want to talk about today is the German tank problem. Has anybody heard of the German tank problem? Okay, only 1 or 2 people. If you've heard about it, please do not speak up, unless it is something that's not related to what you've heard. So, contact information, web pages. If you can't find me in the age of Google, you do not deserve to be able to send me an email. This is not a difficult challenge anymore. Okay. Although getting the clicker to work, that is a difficult challenge. So let me try to reinitialize it. There we go. Okay. So this is a map of Europe. Left is right before World War II starts. Right is in 1942. You can actually click on the link and watch the German armies as they move both east, west, north, and south, and just see how fast they are expanding. There are many reasons for their rapid expansion. One of it is the terrific use they had of tanks in battle. And so they had terrific ideas on how to use them. And it was extremely important for the Allies to figure out how to counter. Any of you ever see the movie Patton? Okay, Patton has one of my favorite lines in all movie history. So the great US General Patton, who I'm unfortunately related to through marriage, beat the Germans in a battle in North Africa. And he has a beautiful line. Rommel was the German general. You magnificent bastard, I read your book! And so after World War I, Rommel, who was a lieutenant, had written a book about tank tactics. Okay, word of advice, if there is a chance you might be involved in a battle with someone else, do not write a book that describes in great detail how you like to use things. So, a lot of this talk is related to cryptography, to keeping certain information secret. Broadcasting how you like to use your tanks in battle, not necessarily the smartest thing. Now, the Allies really wanted to know how many tanks were the Germans producing and how many tanks were they putting in various stages of war. So, here's a picture of German tank production. So, how can we find out the number of tanks? Well, one idea is to contact the Germans and say, excuse me, we're trying to plan our counteroffensive. Could you please tell us how many tanks you're making and which states you're going to be deploying them to and when? Okay. This will probably not result in an accurate answer. Any thoughts as to how you might get an idea of what the true number is for tanks? How can you figure it out? Yes?
Keep track of how many tanks you think you're destroying and the total number you can see.
Good, so one is to use mathematics and stats, is look after each battle and see what tanks are there. What else could you do?
Fly an airplane over and just see.
So one thing is to try to fly into Germany or relate to that, send agents into Germany and try to gather information. So it's spies versus math stats. This is going to be probably the easiest marshmallow I can give you. Based on the fact, this is conditional probability, that I am giving this talk in a math program and not at the CIA, NSA, something like that, who do you think does a better job, the spies or the mathematicians and statisticians? Yeah.
We sent a spy to find out which the answer was, and the answer that you decided on was math and stats.
Excellent, excellent. So this is your classic leading question. So math stats does better. So here's the general framework of the problem. Let's assume you observed serial numbers S1, S2, all the way up to SK. So you observe K tanks on capture to destroy tanks after the battle, and you want to figure out how many tanks were produced. Okay, this is the original version of the German tank problem. So let's make it a little bit more explicit, a little bit more mathematical. Let's assume, just to make anything easy, that the tanks are numbered from 1 to n, consecutive, serial 1, 2, 3. You observe K, and you want to figure out what the largest one is. The new version, which I will talk about a little bit today, which amazingly I have not been able to find in the literature, is instead of starting at tank 1, you start at tank N1. Anybody, if you ever walk into a gym, you hear someone go, 195, 196, or maybe 503, 504. You start off with numbers to hide how many you're doing. Or if a company is selling a product, congratulations, you bought product number 2. That might make you a little concerned if you were buying a number with that low of a serial number. Ooh, product 2014, this looks like a popular item. So there's a lot of stuff like this where you try to hide how much has been done. So there are logical explanations for why you would number things 1, 2, 3. First of all, people have thought that you could try to glean information from this. The second is it's really nice to have the numbers labeled from 1 to n. If they are labeled sequentially. You can actually tell what order things were produced. Or you could have your numbers being, different code digits. This is maybe the month, this is the day. It gives you some idea of when you might need to do certain maintenance on the tank. So there's advantages to having it straight out and not having it in code. But nowadays, a lot of products online are coded, so people do not know how many, or better yet, how few things have been purchased. What we want to do is we want to come up with a formula to estimate the number of tanks as a function of M, the largest serial number we observe, and K, the number of tanks we observe. Can anybody give me a simple property that our estimate must have? What can you tell me about N as a function of M and K? It's got to be at least one. Yes? Yes, it should not be smaller than M. Right? If you observe a tank with serial number 23 and you believe the tanks are numbered sequentially, you should not guess that there are 15 tanks in the theater. Right? This hopefully sounds humorous, but this idea of trying to look at extreme cases is exceptionally valuable in mathematics. Push things to the extreme limits, and that will give you some idea of whether or not the formula is reasonable. Now, there's dangers of underestimating and overestimating. Anybody want to give me a danger of either one? What would be bad if you overestimate? What would be bad if you underestimate? Yes?
If you overestimate the investment in resources, it's not.
Yeah, so if you overestimate, you could put in far too many resources for battle when you don't really need it. We thought they had 1,000 tanks, they had 2, okay. Or you might even be analysis by paralysis. You might not even attack, no, that's too well fortified. The danger of underestimating, you might think, they only have 2 tanks, you launch 20, and all of a sudden you see there's 250 arrayed in front of you. One of the classic examples of this is from the Civil War. There's many different versions of Lincoln's quip. If General McClellan isn't going to use his army, I'd like to borrow it for a while. Where the Army of the Potomac was just, McClellan was the commander, and he was, oh, the South has too many forces for us to attack, we gotta wait, we gotta get more troops. And the Union missed numerous opportunities to engage the Southern Army when they had numerical superiority because of overestimating. So I will talk a little bit about the mathematical preliminaries. Depending on how much people know, we're spending a lot of time or little time on some of the binomial identities. Then I'll talk about the original formulation, maybe talk a little bit about the new formulation, and then talk about some interesting issues that arise when you try to use statistics. So I've seen that some of you have done statistics, which is wonderful. This is going to be the century of data science. When I was at Ohio State about 15 years ago, one of the quotes I heard in a data analysis seminar is the weather satellites beam down more information every day than is in the Library of Congress. And we have a couple of hours to use this to make reasonable predictions about the weather. There is so much information out there right now. You need to find good ways to use it in an efficient manner. All right, so has everybody seen factorials, binomial coefficients, and the binomial theorem? If not, everybody's willing to just nod and we'll move on? All right, so I assume everybody's comfortable with that. Pascal's triangle, everybody comfortable? If not, you do have to speak up. If you do speak up, almost surely somebody else will be happy that you did so. But I don't want to do things that I'm sure you've done many times. So the identity we need is n plus 1 choose k is n choose k plus n choose k minus 1. There's several proofs of this. One is the brute force algebra. Just expand, cross multiply, and show that it works. I prefer the proof by story. So imagine you have n Red Sox fans, and unfortunately there's one Yankee fan around. And you want to form it's probably true. Now, Mets are fine. I actually have several students who are working with the Mets right now. Mets are great. You have n Red Sox fan, one Yankee fan, and I want to choose a group of k people from these n plus 1 people. Well, the left-hand side, so all of combinatorics is counting something 2 different ways. If I want to choose k people from n plus 1, it's just n plus 1 choose k. Or I can condition on whether or not I have the Yankee fan. So in the first happy situation, I don't choose the Yankee fan, so it's 1 choose 0, and then I have to choose k Red Sox fans. Or I choose the Yankee fan, 1 choose 1, and then I have to choose k minus 1. I'm sorry, I choose the Yankee fan, and then I have to choose k minus 1 Red Sox fans to get up to k people total. So this is proof by story. Okay. Next thing I need for Pascal's triangle is a diagonal entry. So if you had 1 plus 2 plus 3 plus 4 plus 5, that's 15, which is 15 right here. 1 plus 4 plus 10 is 15, which is 1 here. 1 plus 5 is 6. So as you add diagonally, it's related to something one thing over. So I will prove that in a moment. How many of you have actually seen that identity? A good number, but not everybody. How many of you have seen this one? Right. This has absolutely no relation to the talk, but it's just so beautiful that it would be wrong not to do it. Okay? So what I'm doing is for Pascal's triangle, I'm putting a dot if the number's odd, and I'm deleting the number if it's even. And rather than having Pascal's triangle start at the top and go down, I'm having it start at the side and go like this, because when I graph things are better graphing like this. Due to budget cutbacks, which is sadly an issue at this institution, I believe I am not allowed an infinitely large board, correct? So we have to keep it onto the screen. All right, no problem. What I will do is I will just keep zooming out, so we'll always keep the triangle in the box. So as we add more and more rows, I'm going to just make things smaller and smaller and smaller, and this way we'll always see it in the same box. And this is what happens as you take more and more rows. Does this shape look familiar to anybody? Yeah, so what is this? It's Sierpinski's triangle. So if the toggle works correctly, so this is a program I wrote in Mathematica to just keep zooming out and adding more and more rows. So as a nice exercise, write a little program to do this. This is not the most efficient one possible. There's actually audio. I'm saying very interesting things right now as the mouse moves back and forth. You can look at the link later. If you've seen the beginning of Star Wars with the Imperial Star Destroyer coming, it's very similar, I think, to this right now. And that's Princess Leia's ship over there about to be. Okay. So this goes on for a while. We don't really need to see any more of that. Okay. So here is the other identity. The sum of m choose k, m goes from k to n, is n plus 1 choose k plus 1. And when you see something like this, what is your first thought about how you should prove it? Any thoughts? So you fix a k, and m goes from k to n. What might be your thought as to how you would prove this? Yes? Induction. So this is a clear, let me try to do it by induction. So if k is fixed, if we choose base case n equals k, it's very easy, you get 1 equals 1, and in the inductive step, you assume it's true up to n, substitute in, add the next term, and then Pascal's identity just gives it to you. When you are doing mathematics, you always want to know why does the miracle happen? Why does everything come out nice in the end? In general, it is very hard to get a closed form answer. Is there anybody here who's willing to admit that they're interested in economics? The dark side. Okay, we've got a couple of people. So, well, I wouldn't say that. This is being recorded. So, for those of you in economics, if you go far, it's very rare to have a closed form solution. It would be wonderful if we could say, let's change the tax policy by this and change this, and let's see what happens to the GDP. What you end up doing is you do lots of simulations because things are very complicated. If you can have a nice closed form expression, that's wonderful. You can then see the effect of each little thing. And it's the fact that we have this identity here that's going to allow us to get a closed form solution to predict what the best value of n is given m and k. It's because we have a way to evaluate this sum and reduce this long sum with just one term. Right. So let's get into the theory now. Anybody want to say a little bit about how our guess should depend on m and k? We agree that it has to be at least m. Right? If we observe m is the largest serial number, we better guess that there are at least m tanks being produced in the field. So let's write it as m plus g of m comma k, some little boost. And I'm going to say the simplest guess is b times m divided by k. Does that seem reasonable, where b is some constant? So what's good about this formula? Yes?
The more tanks you see, the lower the guess is.
Yeah, so the more tanks you see, the larger k is, the lower the inflation is, the lower the extra thing you're adding. Which makes sense, because for instance, if k is as large as n, you shouldn't add anything more to it. You should have seen it. Okay, what about the m dependence? As m gets larger, does it make sense to increase your guess by a little bit more? Seems reasonable. The actual answer is m times 1 plus 1 over k, so that b would actually just be 1, and then minus 1. Anybody see Indiana Jones and the Raiders of Lost Ark? Yes.
This probably should be self-explanatory, but n with the little
And hat is our best,
is
our
the
best
number
guess.
of total tanks that the Germans have.
Right, so capital N is the number of tanks the Germans have, and then n hat is our best guess for the number of tanks the Germans have based on what we see. So is this formula reasonable? Are there any values of m or k that we could test? What would be a good value of m or k? Maybe, yes.
Let just the maximum, let's just say you observed all the tanks.
So let's say k equals n. If k equals n, we would hope that our guess would be n. Well, if we take k equals n, we get 1 plus 1 over n. M has to be n, because we've observed all the tanks, minus 1, it actually comes out to be n. So things are perfectly good when k equals n. And if you take k equals 1, you would basically say my best guess is I take the maximum observed, multiply it by 2, and subtract 1. Essentially, you double. Well, if I observe one tank between 1 and n, it kind of makes sense that the value I guessed was right in the middle. So doubling it seems reasonable. This is not a proof, but it's a quick sanity check that these are reasonable answers. Okay, so now there's two different ways to prove the key lemma. So I want to calculate what is the probability if we have n tanks and we observe k of them, that the largest serial number is m. There's two different ways to do this. The first is, if m is less than k, the probability is 0. If I observe 15 tanks, and they start at 1 and they're labeled sequentially, I'm not going to observe a large tank of 13. So the probability is 0 if m is less than k. It's 0 if m is greater than n. If there's only 100 tanks, I'm not going to observe a serial of 150. So I only have to worry about m between k and n. And here's two different ways of looking at the formula. The first is, m choose k is the number of ways to choose k tanks whose serial number is at most m. So this is a really nice probability idea. So this is the number of tanks whose serial number is at most m. The next term is the number of tanks whose serial number is at most m minus 1. So if I look at the difference, it will be the number of tanks whose largest serial number is exactly m. The other way of doing it is I say, well, look, if the largest serial number is m, then I have to choose k minus 1 tanks from the first m minus 1 values. So it's m minus 1 choose k minus 1. And I just divide by the number of ways to choose exactly k tanks, which is just n choose k. So these are two different ways to compute the probability. So we actually have a pretty nice explicit formula for the largest observed tank is m. Okay, so now expected value, anybody who's taken any class where you have grades knows expected value. It's the average. You take up all the scores and you divide by the number if everybody's weighted equal. If things aren't weighted equally, if you have a class where the final is 40%, the midterm is 30%, the homework is 30%, the class participation is 5%, you have a teacher who can't add. You just multiply each score by the correct weight. So here what we're doing is we're multiplying the value m by the probability that we got m. So this is a weighted sum, and this will be the average or the expected value of the largest serial number. And so the question is, can we actually evaluate this sum? So rather than hitting slide advance and showing the algebra, what are your thoughts as to how you might try to tackle this sum? You've got m times m minus 1 choose k minus 1 divided by n choose k. What might you do? Yeah.
Use the I forget what's the word, but like what we had before, using that identity.
So one thing is we want to use the identity, but we don't quite have the situation of the identity because we have this extra fact of m. But we are close, and I like the idea of, Professor Miller mentioned this identity earlier. There's probably a reason. Now, I did deliberately do the Sierpinski triangle, which has nothing to do with the talk, just to make sure you don't trust me too much. But I do like the idea of using the identity. We have to get to that situation. So what could we do to try to get to that situation? Yes?
Somehow, could you try to pull an m into the coefficient so that?
Yeah, I mean, look at this. It's got an m minus 1 with the upstairs here, and it's got an m over here. Right? It's really asking to come in. So we should open up these binomial coefficients. So let's open it up. And now the m comes over to the m minus 1. They become a nice m factorial, which is what we had before. And now we just do some algebra by manipulating things. Okay. And so when the dust settles, we get down to here. And here is that sum that we wanted. And now we can do what you said. We just pull all this stuff. This doesn't depend on m. It just depends on k, and it's just a factor. I can pull it out of the sum. And this can be evaluated in closed form. And now what should we do from this point? So what are your thoughts? What should we do from this point? Yes?
Do you expand the choose on the right?
Yeah, if we expand the choose on the right, so n plus 1 choose k plus 1, we put what it in is, oh, I got an n plus 1 factorial, I have an n factorial down here, massive death and destruction, things cancel, and you have a really nice clean form. So I just want to talk a little bit about algebra, and I'll try to hold this over here to just, so how many people are cube enthusiasts? All right, we will talk more about cubes later because I have a challenge, but it requires all of you to keep a secret until sometime in January. All right, who here can solve the cube? Okay, excellent. But not that many hands went up as cube enthusiasts. Interesting. Okay, so the cube has lots of ways to turn it, correct? Anybody who learns cubes for me learns to do the red side first, or in this cube, the pink side, okay? Is it easy or hard to identify which is the pink side? All right, not much of a challenge. All right, these two cubes, let's hold it up over here like this because it's being recorded, and then later on you can all look on, no, I'll shut up to you as well. So these two cubes are a little bit different. You know, this has a strange cross pattern here, but it at least is 3 by 3 on the sides, even though they're different shapes. This one's actually 2 by 3 on the sides and has an even stranger cross pattern here. What is Hampshire College's weapons policy? Because with a few turns, I can turn this cube into like a little nunchuck. I, of course, would never do this through airport security. I actually do cube artwork, and I had a 10 by 10 cube that I had done with Fibonacci art as I was going to a Fibonacci conference. And for a while, it was unclear if security was going to make me solve the cube to prove that this was not dangerous. This cube and this cube turned out to be almost the same as the 3 by 3. It's the same as the 3 by 3 with pictures on the side. Okay. Can anybody see a side when I'm holding it like this? Does anybody see a side of the cube? No, you do not. This is not a side of the cube. When I try to turn this, it doesn't turn properly. You have to hold it at a 45-degree angle. This is now, I'll try to hold it like this. This is now the front face. Okay? These are the two sides. And if you hold the cube like this, it's essentially the same. This one you have to hold it like a 30-degree angle. This is the whole point of algebra. This difference between these is really what all algebra is about. Can you find the right way to look at the expression? And if you find the right way to look at the expression, then you can often reduce the algebra to get a wonderful closed form solution. Sometimes it's easier than others to figure out what is the right way to look at it. But this is the real challenge. And once we have this, we're in great shape. So we know the expected value of m, the largest serial number, is k over k plus 1 times n plus 1. So let's just solve for n. So n is the expected value times 1 plus 1 over k minus 1. So we substitute m, our best observed value for m, and we get our formula. So the algebra is not that bad. And so now it all comes down to who do you think did better? So we agree that mathematicians did better. Do you think by a little bit, by a decent amount, or they just blew away the spies? We will save that for a little bit later. So, what if we try to generalize the problem? So I'm not going to go into too much detail here. It's pretty similar. All we do now is we have to deal with the fact that we have an unknown start. And so we think that our formula should be pretty similar. So S is going to be the spread. And we're going to look at plus some function of the spread and the number of tanks observed. And before I did B m over k, now I have B s over k minus 1. So any thoughts as to why it's k minus 1 and not k? So if you know statistics, this might help. If you think of the sample standard deviation. So the spread is the difference between the largest and the smallest observed serial numbers. What happens if I try to use this formula when k equals 1? Am I allowed to use this formula when k equals 1? No. There was actually somebody taken into police custody outside the Math REU program at Williams a few days ago. I told the students it was a division by 0 attempt, and campus security came down really fast and stopped this from happening. I haven't been able to confirm that, but I'd like to believe that we have good agents on campus that will make sure this doesn't happen. You should not be doing anything involving division by 0. If k equals 1, if you only observe one tank, what's the spread? 0. All right, so we would at least have 0 over 0, so it's at least undefined. But you should not have a formula that would predict what's going on if you only have one observation. If you've known some statistics, if you want to try to calculate the standard deviation, how much things vary, if you only have one observation, it's kind of tough to see how things are varying. You need at least 2 observations to see variation. That's why a k-1 is actually a very reasonable guess to put in here. And when the dust settles, you get a 2 over k-1. You can do standard checks when k equals 2 and n. It's going to be very similar. And you might even think the 2 might be coming because I'm now going in 2 different directions. So I'm not going to go through the algebra. I'm going to just pause the slides over here. You can similarly find a formula for the probability that the spread equals s. And then you can go through and you can do the more detailed analysis. So I've put all of that in the appendices. How many of you use LaTeX? All right, so the advantage of using Darmstadt, which is the best city class in Beamer, is I can just quickly click on something over here and move to that part of the talk. And so here's a list of everything, and then you can just go through and do the algebra. The algebra is a little bit more involved than last time, but eventually the algebra ends and you get the formula. Okay, it's essentially at the same level as what we did before, just the algebra is a little bit more involved because we don't know both things. Okay, so I'm going to try to jump back to where we were. Okay, so here is the comparison of spies versus statistics. So the far right column is the German records. We did not have this knowledge during World War II, but after the war, we do have access to this information. You see the intelligence estimates and you see the statistical estimates. So neither the mathematicians, statisticians, nor the spies were correct. However, there is such a thing as relative error. Not all errors are equally. So Isaac Asimov has a wonderful article, The Relativity of Wrong. We talked about people used to think the earth was flat. And then after that, what did they think the earth was? Round, a sphere. And then after that, they said, well, it's actually not a sphere, it's an oblate spheroid. Because of the spinning and gravity, it actually flattens things a little bit along, I think, the poles and bumps it up around the equator. And so some people said, what this shows us is that you can never have the right answer. And Asimov says, no. What this shows us is that there are relativities of wrong. And that you're thinking that the earth is flat is wrong. Thinking the earth is sphere is wrong. But it's not as wrong to say sphere versus flat. And the people who think that there's no difference, they're even more wrong than everyone else. It's a great article to read. So over here, you can see the mathematicians are damn good. Now, the problem is you have to convince your superiors to trust you. This is a whole other talk as to how do you take the mathematics you know and convince the people who can say yay or nay to do what you say. So at dinner, if people are interested, I am actually an elected official of the Mount Baylock Regional School Committee for Williamstown and Lanesboro, and I am happy to talk about the issues of trying to apply mathematics in the public sector. All right, so we still have on the order of a little bit more than 17 minutes. So what I want to do is I want to talk a little bit about regression. This is one of my favorite ideas in mathematics. It's extremely powerful. It can be used for a lot of things. So I've actually used this for school committee stuff. I've used this for some consulting that I've done in various industries. People often feel that they can't do anything useful until they maybe get a PhD and learn all this advanced mathematics. No. The bar is you have to do better than is being done. In many situations, that's a very low bar. You don't have to get the optimal answer. You just have to do better than is being done. That's a good bar to aim for. So what I want to do is I want to talk a little bit about linear regression. So the idea is to find the best fit parameters. You believe that there's some linear relationship between y and x. Y equals ax plus b. And you want to find the best fit values of a and b. How many people have taken calculus? How many people have not taken calculus? Okay, so if you haven't taken calculus, you will have a very quick introduction. So here are 3 different choices of error. The first error is I look at the observed value and I subtract off the predicted. The second is I do the same thing, but I take absolute values. And the third is I do the same thing, but I take squares. Can anybody tell me an issue with one of these 3 methods? Yes.
the issue with the first one is that positive error and negative error can cancel each other out.
Yeah, so imagine I want to find the best fit line that goes to the bottom left of the screen and the top right. Does everybody know what the best fit line is between those 2 points? Yes, you start in the upper left and go straight down to the bottom right, and the positive error here cancels with a negative error here, and you have no error. Okay, so first one is right up. We do not want to do that. So it's now down to squares versus absolute values. And the way I like to phrase it is, if I am being hired to do the analysis, I do squares. If I'm hiring somebody, I have them do the absolute values. The absolute value function is not differentiable in calculus, but the square function is. So if you use the square function, calculus plus linear algebra live in harmony, and they give you an explicit formula for the best fit constants A and B. You just plug things in and it comes right out. If you use absolute values, then you have to use numerical programs to figure out what the optimal values are. But the absolute value, I think, is a little bit more stable in some things. All right, so when you do things down, the way it works is this symbol here means the partial derivative. It means hold B constant and take the derivative with respect to A. The other one in a shock is hold A constant and take the derivative for B. In Calc 1, how do you find where the maximum and minima are? Yes? Damn it. All right, so tell me where I'm moving at my fastest speed. All right. Would you like to refine your answer?
No, we want to see that again.
Thankfully, the camera is in this direction. I should have moved it.
When it may also be undefined.
Not undefined.
Or at least like at the end.
At the endpoints, right? You check the endpoints as well as the critical points. Okay? So hopefully you will never forget this again. In the list of almost surely false apocryphal stories, one of my favorites is the design of the self-bomber stealth fighter, where they didn't check to see if they were maximizing or minimizing. They just looked at the critical point. And they essentially did the thing, we're here playing! Probably false. But I like to imagine that some people did not check and actually had constructed the we're here playing. So always remember, you have to check endpoints. So for this problem, we don't really have to worry, because as you let A or B get very large, positive or negative, you can see you can just drive the error to infinity. So it's really going to be the critical points. So you set the partial derivatives equal to 0, you do the algebra, you get the matrix equation, you can solve it in many different ways, and you actually get explicit formulas for A and B in terms of the values of X and Y. And so the problem with this is most relationships in life are not linear. And so if you can only fit linear relationships, it's a little bit limiting. But there's logarithms. So how many of you have a true understanding of why we care about logarithms? Or does it just seem like sadistic teachers who want to do something? I see like 1 or 2 hands going up. Logarithms can convert many things to linear relationships. So imagine y equals capital B times x to the a. If I take the log of both sides, I get the log of y equals a log x plus little b. Well, let little b be the log of big B. So even though x and y are related through a power relationship, log of x and log of y are related through a linear relationship. So you think of like Newton's law of gravity, if you think of the force and the distance between things, it's a 1 over r squared, it's going to be linear when you look at the log of the force versus the log of the distance. So this method applies to a lot more than just straight lines. How many of you have heard of Kepler's laws of planetary motion? Okay. These were one of the crucial building blocks for Newton. First law, planets move in elliptical orbits about the sun, with the sun on one of the foci. Okay, not so bad. Second one, if you draw a line from the sun to the planet, it sweeps out equal areas at equal times. Not so bad. The last one is the Sesame Street law. One of these is not like the other. If you look at the square of the orbital period of a planet, then it is proportional to the cube of the length of the semi-major axis. All right, well, we could actually take square roots of both sides and go from t squared is L cubed to t is L to the 1.5. And there should have been a hint that this was happening because I called this constant B tilde, which is indicating that something's going to happen to it real soon. So imagine we don't know that this is true. but we expect that maybe there's some law between T and L. Can we find this numerically? So here is a list of the semi-major axes of planets in astronomical units and the orbital planets in years. And I'm guessing T equals BL to the A. Anybody have any guess as to what B should be? Yes. 1, excellent. Earth is chosen to be 1 astronomical unit away, whose period is essentially 1 year. So I'm choosing units to essentially make B equals 1. There are a lot of wonderful units. There are the Bruno, the millihelen, the slug, the smoot. I might talk a little bit about the smoot in a moment. I think I have a slide on that. There's a link to a bunch of humorous units of measurement. A non-trivial percent of these come from MIT. So let's plot the log of T versus the log of L. And so I have unfortunately followed modern convention that there are only 8 planets. It pains me to do this. I actually have a friend who was friend with the person who hit enter and downgraded Pluto's status. They were the one who had to do it. So if you look at the data points, that's a pretty good line. And if you look at the slope, A is 1.49986 and B is essentially 0. You want to talk about a phenomenal fit. And remember, little b is the log of big B. I feel like Dr. Seuss. Big B is 1, the log of 1 is 0. So this is strongly supporting our belief in the values we get from Kepler's laws. So I'd mentioned smoot. Anybody know what bridge this is? Yeah, it's the Harvard Bridge. This is right there. Okay, this is not the hard part. So smoot was a pledge at MIT. And there are limits to what you can do to your pledges, but they are very generous limits. And so in the interest of science, they decided to answer the age-old question, I wonder if we took one of our pledges, how many times we'd have to pick him up and march him down the bridge before we got to the other end of the bridge. So the bridge is 620.1 meters, or 364.1 smoots plus or minus an ear. Love the way they give their measurement. The Cambridge police and city did not find this amusing, and so when the MIT people did this, they actually put down little markers so that they would know where to put Smoot down when they picked him up. And so these were erased. Well, damn it, that can't happen. So they took Smoot and they did it again. And this went back and forth, and eventually, it's hell with it. And they let the Smoot mark stay. And now it's been institutionalized. If there is an accident on the bridge, they report where the accident was by its Smoot measurement from the edge. At the end of the talk, we will see what happens to Smoot. All right. How many of you have seen the birthday problem? How many people do you need in a room before you have a 50% chance? So in this room, should I be confident? Yeah. So years ago, I was asked by Williams to entertain a bunch of prospective students, and I decided to have some fun. So I got the director of admissions to agree that if there were not 2 prospectives who shared a birthday at the dinner, that everybody at my table would get free admission to Williams. Now, there were over 100 people in the room. I was not worried, if you know the problem. I did not tell my wife at the time that I was actually going to be liable to some of the financial aid if this actually happened. I showed the director of admissions my calculations about how unlikely it is, and I got him to sign off on this idea. So, as you would expect, I was very safe. So you need on the order of around 22, 23 people. You can generalize the problem and say, imagine you have D days in a year. How many people would you need? And so it turns out by doing a little play, you can get that it's roughly D to the 1/2 log, square root of log of 4. The analysis is not too bad. If you want to see, just send me an email. You can do some simulations. And when you do a scatter plot and you try to do the best fit line, I did it 10,000 simulations, D chosen randomly from 10,000 to 100,000. And I got 0.506 for one, 0.48 for the other, very close to the exponent of 1/2. Now the B's aren't quite as good, they fluctuate a little bit more. It turns out that you're more likely to get A correct than you are to get little b. Which if you only could get one correct, you want the A because that's going to give you how things scale. Okay, so this is trying to plot what's going on with the German tank problem. This is one of many. I'm not going to go into too much details here. I'm going to go into the other ones. But here is a good 2-dimensional plot using logarithms and plotting the log of the number of tanks versus the log of m and 1 over k. And you can see a phenomenally good fit. You can see, instead of the generalization of a line, you now get a plane. All right. So I want to just end briefly with implementation issues. So here I'm trying to find the best fit line. Theory tells me n is 1 plus 1 over k times m minus 1. Imagine we don't know that, and I want to plot, and I want to try to sniff this out. Well, what I can do is I'll choose a couple of values of n, I'll fix k, and I'll sample from n without replacement, and I'll write down the largest serial number, and I'll just plot the maximum observed versus n. And I can do this. And when I do this, I get 0.784m plus 2875 for this range. Do you think this is a good best fit line, or does this have an issue? So one of the best quotes I've ever seen in a textbook was my high school physics book, where it was talking about some of the strange results of special relativity. So if you're on a train, and the train is traveling 100 miles an hour, and you're jogging on the train at 5 miles an hour, how fast do you look to somebody on the ground? You're going in the same direction the train is going. How fast does it look like you're moving?
A little bit less.
Oh, no. Whoever said a little bit less than you're being a smartass. That's a technical term. I said, how does it look to somebody on the ground? I didn't say, what is it? How does it look to someone on the ground? It looks 105. The actual answer is slightly less than 105 because by special relativity, speeds are not quite additive. But at normal terrestrial speeds, you will not notice a difference. You have to be at an appreciable fraction of the speed of light to see a real difference. So if you have a train traveling at 3/4 the speed of light and somebody's jogging on the train at 3/4 the speed of light, they do not seem to be going 1.5 times the speed of light. And the textbook said, these results seem counterintuitive, but you have to remember, most people don't have experience traveling at 3/4 the speed of light. And I like the use of the word most. But something should look wrong here. If I try to extend this formula, do you like n is 0.784m plus 2875? Why not?
Like, m is really low, then n is still like almost 3,000.
Well, okay, so if m is really low, it's going to be dominated by that constant term. That's one thing that's bad. What else is bad?
If n is really high, then 2,875 is not going to make up for the less than 1 n's that we have. So
Yeah.
n is going to be less than m.
Right, so if m is tremendously large, this is much less than m. So, I would observe the largest serial number is 100,000. I'm going to guess that there's 78,400 tanks. So this has to be wrong. Well, let's try k equals 2. So the best fit line is now 1.5 and we get 0.96. It's bad. It's not as bad, but it's bad. Let's try again. K equals 5. We get 1.2. The best fit value is 1.03. Okay, at least it's now greater than 1. It's getting better, but there's still issues here. And so what I like about this is that when you try to do the theory, there can be real implementation issues. And there's a nice, good, subtle reason, which I'll let you ponder a little bit, as to why this is doing such a bad job. But you should know enough that whenever you see data, you should ask, is this reasonable? And seeing a value, seeing the coefficient of m being less than 1, that should not be reasonable. Now, there's a couple things we can do. So one thing is I could try doing it the other way. I could plot m as a function of the number of tanks, and that actually does much better. And now you would have the reciprocal relationship. It should be 0.5n, I'm getting 0.496. That's pretty good. So flipping it like that actually does a really good job. This is now doing k equals 2. Again, 0.667 versus 0.668. Outstanding. 5, 0.883, 0.828. Again, very good. Here's another thing to do. I can plot as a function of the maximum observed serial number n. And now what I'm going to do is for each value of n, I'll do 100 ones and I'll average them. And when I do that averaging, now it's much tighter, and now I get a really good fit. There's a lot more you can do. We can do this analysis and find the best fit straight line for each value of k. Let's do k equals 1, k equals 2, k equals 3, and we'll plot this. Does that look like 1 plus 1 over k to you? Maybe. But how could we try to figure this out? Well, we could take logarithms. Well, we know that there's got to be at least 1. We could subtract 1 and take logarithms. And so when we subtract 1 and take logarithms of the best fit constant, we now get a beautiful straight line, and the coefficient is negative 0.999. That's really, really, really looking like 1 over k. So this is the power of statistics. We can do these very simple calculations and get a really good sense of what is going on out there. All right, so here's a couple of references, but first I want to talk about seizing opportunities. So I've mentioned that I was going to tell you what happened to a certain person. Anybody remember the name? Anybody want to guess what Smoot did with the rest of his life? Do you think he was scarred from this experience? So this is Smoot in his older age, chairman of the American National Standards Institute, president of the International Organization for Standards. You can't make this up. I'm just imagining the job application. Well, I don't like to brag, but I am a unit of measurement. So you never know where things will lead. You want to distinguish yourself. You want to find a way to make yourself different from what other people are doing. All right, so I'm going to just quickly stop the screen share. I'm going to stop the recording.